Hello and welcome back to another Calculus 3 video. This is going to be the fourth part in our series of quadric surfaces. We are going to be looking over the quadric surface of hyperboloid of one sheet. We will get into what that means later on. But first of all, let's just go ahead and review one more time what the quadric surface is. Quadric surface is a graph of a quadratic in three variables. How we are going to plot these is we are going to start by plotting the intercepts, we are going to plot the traces, and then we are going to complete the picture from there, fill in the dots, so to speak. Today we are going to be covering the hyperboloid of one sheet, given by the general equation of x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. This looks pretty similar to an ellipsoid, except as you can notice, we have a minus here. That is what makes it one sheet. I will get into how many sheets there could be. Spoiler alert, we will get to two sheets where we have two negatives, but one sheet is going to have one negative here equal to 1 or some constant. That is how you are going to recognize whether it is a hyperboloid of one sheet or two sheets or even an ellipsoid you may confuse it with. Without further ado, let's go ahead and get into an example. We are asked to graph x squared over 4 plus y squared over 9 minus z squared over 25 is equal to 1. Let's go ahead and go over our strategy here. We have 3 steps. We want to plot our intercepts. We want to plot our traces. And we want to complete our photo. Let's go ahead and do step 1. I'm going to color code this one. So, for our x-intercept, we are going to set our y and our z equal to 0. So now we have the equation x squared over 4 is equal to 1. Let's go ahead and multiply that 4 out, do some simple algebra. We have x squared is equal to 4. Take the square root of both sides. We have x is equal to positive or negative 2. That is going to be our x-intercept. Let's go ahead and graph it right now. X-intercept, 1, 1, 2, we'll call it, we'll stretch it out a little bit. This is going to be our x-intercept right here. Negative direction, we're going to have it right here. These are our two intercepts. Let's go ahead and do our next one, and we'll do whatever this like salmon kind of color is, perhaps. Y-intercept, we are going to set our x and our z equal to 0, meaning we have y squared over 9 is equal to 1. Let's go ahead and write that down. Y squared over 9 is equal to 1. Multiply both sides by 9. We have y squared is equal to 9. Take the square root of both sides. We now have y is equal to positive or negative 3. Go ahead and plot those as well. 1, 2, 3. We'll call it good right here. Let's go just a little bit further out. Yeah. Eyeball that over there. That was pretty good, actually. Oh, I'm getting good at this, actually. Z-intercept, doing red. Spooky. Z-intercept xy equal to 0. We now have a negative z squared over 25 is equal to 1. We are going to multiply 25 out by both sides. We have negative z squared is equal to 25. Oh no. This is no solution. We cannot square some value and make it negative and have it be positive. So this has no solution, meaning what? There is no z-intercept. And this is not a scenario where we are going to want to. I'll get into it. Never mind. No solution, meaning what? We have no z-intercept. Looks good. Bang. Plotting our intercepts is done. Step number 2. Let's give ourselves some more room for this one. Step number 2. We are going to want to plot our traces now. In typical fashion, yeah. We are going to do our xz trace. We'll start with let's do our XY trace. I like to go in order. xy trace. Go ahead and set our z equal to 0, meaning we have x squared over 4 plus y squared over 9 is equal to 1. That is going to be our xy trace. Now we have our yz trace, wherein we set our x equal to 0. So now we have y squared over 9 minus z squared over 25 is equal to 1. Y squared over 9 minus z squared over 25 is equal to 1. So our last trace here, we're going to have our xz trace. Setting our y equal to 0, we are going to have x squared over 4 minus z squared over 25 is equal to 1. Sounds good. Now we have our 3 traces, but when we graph this, we have hyperbolas, right? Okay. We need, essentially to make it a better photo in my eyes, we need to set our xy trace equal to our z equals z naught trace. I'll verbalize it once I graph it, but this is just kind of one of those things where it's like, it's difficult to explain why we set z equals z naught when we do. I guess what you could say for this is the xy trace is the only trace that is not including that z term, meaning we do not have a negative in there. So what would happen essentially when we do our z equals z naught trace, we are going to have that x squared over 4 plus y squared over 9 minus z naught squared over 25, I think, equals 1. Since this is a constant right here, we're just going to add that out. Y squared over 9 is equal to 1 plus z naught squared over 25. Meaning, it's the same concept wherein we have our circles. We can have circles in the xy plane going all around this, and that's something that we're really going to need when we graph this. I can't verbalize why easily, so just understand that that's why I'm doing this, is so that we can have ellipses circling the graph. Let me take a sip of my drink before we go ahead and start graphing this bad boy. Alrighty, so our xz trace, where are you? What color did I use for that? Green? Green. Xz trace, meaning we are going to forget this right here even exists. We have x squared over 4 minus z squared over 25 is equal to 1. So that is just going to be a hyperbola. That is the equation of a hyperbola, meaning we can do... How am I going to draw this? Might be a little bit... we're not going to draw that one first. I lied. Because that one is kind of dependent on how well I draw YZ trace. Same thing, that is going to be a hyperbola. This one's going to be easier to draw. It's going to... there we go. You know what? I'm actually going to... Let's see. Will you do that nicely? Yeah, that's nice. Yeah, that's really nice, actually. Okay. Just pretend I put that on the intercept first try. There we go. That's actually quite nice. Spectacular. YZ trace is done. XZ trace, we're going to forget that this exists right here. Oh man, this is where it goes downhill. We're going to make this baby real steep. Oh man, don't make that. Okay, you know what? It'll do. Just make that. It's a little bit more curved than it needs to be, but... Oh my goodness. Alright, we're freehanding this one. Cool. You know what? I would have loved my X to be a little bit more tilted, but that's okay. Our Z equals Z naught trace. Well, first of all, I just want to recognize that if we did graph our x squared over 4 plus y squared over 9 is equal to 1, our xy trace, that would just be this right here. That would just be connecting all our intercepts in our in our lines, okay? So we can already kind of visualize that we needed to do an x equals or z equals z naught trace just by that. So you could, in theory, I think, do a z equals z naught trace afterward, after the fact that you see, all right, that's an ellipse. We can just go ahead and do these all around. So meaning what? We're just going to do that all around. This is our z equals z naught. Let's do one more up here. So, as you can see, we kind of have like a nuclear shape, like a nuclear power shape, right? So then we have like something kind of like that, right? From a two-dimensional standpoint, of course, but it kind of looks like that, okay? That is going to be our hyperboloid of one sheet. We are over halfway done with our quadric surfaces now. So next video, we'll be covering what happens when we have two negatives within our equation. Thank you for watching.